I'm going to do 8.3, then chapter 9, some sample problems, and that's about all. I'm going to do it. And appendix, I want you to read, of course, in your leisure time. Some I'll point out, there's not much to talk about it, but you have to sit down to read. But this section is kind of a last section to review the DDAM, Dynamic Design Analysis Method Procedure. If you miss it here, then you will miss it forever. It's a little bit tricky, so that's what I want to point out. DDAM procedure, you consider the shock excitation one direction at a time, because you're not going to consider the shock in all three directions simultaneously. Then it's going to be too much, too conservative. When you design the building, you do not design for the loading with the earthquake and the gust wind and hurricane or typhoon all at the same time. You don't do that. There is always possibility to collapse. That possibility of the failure or probability of the failure is very small. Usual building is something like a 10 to the minus 6 power. So we are living in really finite world. So always statistics are in behind of us, okay? Which means there is a consideration. Yield stresses, I think I don't know whether I mentioned yield stresses, 36 kips per inch square. In megapascals, I want you to think. There is no such a thing as a particular number, 36 kpsi. But there's a design value. Always you have to look at the data sheet, what that really 36 kpsi means. So it's a design, maybe design stresses, maybe yield stresses, maybe safety factor is already counted. So don't just accept as is, okay? So there is a probability here in the shock. You consider applying the shock one direction at a time. There is only three directions, no rotational components, because when explosion occurs, the shock wave hit the target, shock wave hit the ship. So authorship direction and forward and after direction and the vertical direction at the one direction at a time. But doesn't matter. I use here DDAM. We use coordinate, not X, Y, Z. All this in my notes, they use X1, X2, X3. Doesn't matter. Who cares, right? Doesn't matter. You can pick X1 in vertical direction. Hassan could pick X1 as authorship direction, but keep the right-hand rule. That makes it simpler later to determine the sign in directions, okay? First, step-by-step procedure. First step, idealize the physical system into the n degree of freedom, a discrete system. So you're dealing with a continuum system all the time. So what does it saying is apply the finite element method. Some of you I saw taking the FEM course, so I really encourage all of you to take the course by Professor Lee, right? So break it down into pieces, node and element. Break it down into pieces. And compute the mass and stiffness matrix M and K of the discrete system. So you have to get involved in FEM. Simply speaking, after you to break it into the pieces, then you have to construct the mass matrix. Another word is equation of motions you have to build, then express as a matrix equation of motions, then mass matrix and the stiffness matrix. You have to get it. No damping. You do not need a damping matrix here. So then solve eigenvalue problem. To determine what? To determine? Willis? Natural frequencies and corresponding mode shape. Omega j, that's a jth the modal frequency or natural frequency, and the corresponding mode I use notation phi. And doing all this, if you have something like Abacus or Nastran code or ANSYS code, or there are a lot of code already available in the school environment, all that, then you can use it. In the research institute, they have their own. Sooner you might have a Nastran code. So a lot of different commercial code or school code. SAP SAP is UC Berkeley code. It was readily available to anybody. Okay? Then if you have that, then all you have to do is perform the free vibration analysis, in other words, the modal analysis, or solve eigenvalue problem, all same, to determine the natural frequencies and the corresponding mode shape. It's important when you conduct the dynamic analysis, do that first. Basic idea is to understand the behavior of the system. Same as human relations. Before you really get married, go out, date, to understand whether the personality is a fit between the both people. It's kind of very important. That's another reason is decouple the system in the process, throw the physical system in physical space into the modal space, then it's all decoupled in the modal space. Then just to solve a single degree of freedom, sort of the single mode system, then throw back into the physical space, get the result. That's another reason. Once you got that, and of course mass matrix is what you need, then you need to compute the participation factor. You have to really do a little bit, not a little bit, really review the material on DDAM. I haven't quite decided yet. I might give you one problem in DDAM out of 4 or 5. So here, alpha, you remember alpha? Anybody remember alpha? Alpha times z double dot, remember? On the right hand side, visualize minus m matrix times alpha matrix times scalar quantity z double dot. Alpha, you see, I have done that already. So alpha, this is alpha. How many entries? You usually have 3 entries. This is like x1 entries, x2, x3 entries. If you have excitation, if you consider excitation in x1 direction, you can set x1, let's say vertical, then all the component in the x degrees of freedom, this is the degrees of freedom, all 1, right? All others are 0. All others are 0. So you end up getting the modal participation factor. The reason is to really see how much the right hand side contribute to the total response. The right hand side means it's really loading. So then I mention here, listen carefully here, phi ij and 1. 1 means I said red mark and say x1. x1, this is excitation axis, okay? So see, if I put a phi matrix here, you have rotation component is not in. You pick out after formulation, you get the natural frequencies, mode shapes, and all that. It affects, the value affected by the rotational, the mass moment of inertias and all that. So now you have that. So this is a degree of freedom system. This is number of mode. So here you have a submatrix. First, this is like x1, this is x2, this is x3, means all this, the row means degrees of freedom, all in x direction, x1 direction, because you have a whole bunch of nodes in your system. You pick out all the, you have a whole bunch of nodes, right? Each node has x1, x2, x3 degrees of freedom. Then, of course, you have the mode shape matrix value. So this is all degrees of freedom. This is all x. This is all y. So this is phi x1. This is phi x2. This is phi x3. And this is a mode. How many mode? How many mode? M mode. M is less than or equal to n. Depend on number of mode you selected based on the 80% criteria. Usually pretty low number. And here you assume, I assume excitation is the x1 direction, then it's going to be x1. Then phi ij is there. This is all the summation of x1 direction, x2 direction, x3 direction. But this is expanded form. I'm not sure whether I put here. This is a matrix notation here. This is a jth mode mass matrix alpha. This is for x1. So x1 entries are 1. The x2 entries, x3 entries are all 0. That's why you have only that components are in. If you have excitation in x2, let's say that's the authorship direction, this will be x2 for that mode. So that you have to be kind of careful. All otherwise is very straightforward. So that's the notation the DDEM procedure has been using. And MJ is the same thing, very similar. So this is x1 here, 1, 2, 3 there. Then step 6, multiply G. Check out the 80% criteria to determine number of modes. Then step 7 is shock design value, which is really acceleration value. DJ should not go down below 6, the 6G, okay? Then calculate the effective static force Fij. I is equal to 1 to n. N is the total number of degree of freedom. And J, the n, J goes from 1 to n, 1 to m. M goes the maximum number of mode to include in the analysis. That's about it. Then apply NRL sum, things like that. You remember, this is strictly speaking not correct, right? You have to do every row. Every row you have to do. You remember in chapter 7, the last page supplement? Okay, so now this stuff I want you to read. Elastic shock design value. All this component has to be elastic component. You have to determine whether this is elastic component or whether this is elastoplastic component. Ship spec is going to tell you when you deal with the actual ship. But this is guideline is all here. So just to read if you have a time, at least up to here. Well, I think read up to around here would be good enough. Should read. And failure, this is really failure criteria. Anybody who took the machine design class should know. This is so-called the von Mises stress. Anybody heard about the von Mises stress? You should hear about that. Okay, this is a totally, you don't have to read. But if you have a leisure time, you can turn the page. Okay, 8.5. So, and chapter 9 is 3 sample problem. First 2 problem is a single degree of freedom system, and third problem is 2 degrees of freedom system. So this is a single degrees of freedom system. The reason is this is a whole mass here. And this channel is acting as a spring, very stiff spring. So this is typical example for a single degree of freedom system, and dimensions all there. Then you have to check whether bolt will stay right. If it's not right, what size of the bolt you have to use, what spec. Do you need a high strength bolt or regular bolt, and all that. One of the best book for machine design is Shigley's book. You heard about the machine design book written by Professor Shigley? Very classical book, but now he's gone for some time. So the co-authors have stepped in a few different times with a few different persons. So best edition is the third edition. That's original edition. So if you can find, get the third edition. Otherwise, the sixth edition is the most latest one. Too thick. I hate the book which is too thick. Thin book is better. Always, I love that. Anyway, so this is the case we're gonna do. Okay. Then this is all the input information, the information or data, none, before you really check the shock adequacy. So assumed here, just for example, shock is applied in the vertical direction. Of course, you have to check in the authorship direction. Then you can immediately think about whether bolt gonna be shear out or not. In the vertical direction, whether bolt is not going to fail by the tensions. Okay? And the forward and after direction for this case is also you have to do, but which is about the same as the authorship directions, because it's the shear actions. And the data I selected here is equipment weight is 5,000 pounds. The foundation weight means this channel, so 720 pounds per beam. Equipment location is a deck. Category of shock design value is elastic. Foundation material is all steel, carbon steel, or just simply the construction grade steel. Or you can use high strength steel, but which is a lot expensive. Then going through the procedure. So step 1 is mass and spring. Step 2, for shock in the upward direction, the stiffness of a 6-inch high channel, then stiffness. So virtually you got, what you have here is simply this, single degree of freedom system. But you have a 2 spring. You have a 2 spring side by side. So if you have a 2, let's say K1 and K1 by the channel, so if you total spring stiffness is 2 times K1, right? This is 2 times K1. It's not connected by the serial. This case is different. If this is K1, equivalency K is 1 over K is 1 over K1 plus 1 over K1, right? So you can determine K1 one side Then A is cross-sectional area of the channel times Young's modulus over L. You can easily get that. And A, cross-sectional area, is if this is a long channel, it's not cross-section this way, rectangular section all the way across. Okay? So which is 36 times 0.258. That's what the thickness, this is the thickness of the web. It's only web times 36 inches long. And times Young's modulus divided by 6. So right here. So the rectangular section all the way across, okay? That's what this A is. Then total stiffness is twice. Then you have 93 times 10 to the 6th power pound per inch. Pretty heavy, of course, stiffness because it's a channel. Then the total weight is weight for 5,000 pound weight of the equipment plus half of the weight of foundation, just assuming half goes to the mass, half goes to the foundation. So you just use your engineering judgment. You don't have to fuss about how many percent goes up to mass, how many percent goes down to foundation. You just divide. I usually divide by half. Okay? Then you got all set. So then you can determine omega n. Then what's the modal participation factor for one mode? One mass, one spring. Whether you like it or not, for bachelor, all you have to do is just jump up and down, right? So modal participation factor, one mode. So it's 1. Modal mass, just by itself. Modal weight, you can compute the same. Then find out the D. Take a look at, so here I said this is surface ship. It's a vertical deck mounted, elastic design. Then if you look at section 8.3, 1396, you can get the reference value of A naught and also V naught. A naught is 55.76 Gs. Then A1, if you look at the table, that's A naught is 55.76. Then you got the reference V naught. Then you have look at table for elastic. Then it's V1 is same as V naught. Then now you are ready to compute acceleration. Multiplying V1 by omega 1, then you have a 294.3 Gs. So then if you compare this value with that value, then you pick the lesser value. Lesser value is, of course, this. Then this, then you pick out the D1 as a 55.76 G. Okay, so now you are ready to compute the equivalent static loading. Mass, phi is equal to 1, only one mode. P is equal to 1. You know D1, you know M. So then you can determine the force here. And you know the force, you know the spring, then you can compute the deformation. Deformation could be compressive or tensile, either directions, okay? You have to consider either direction. Then you compute the axial stresses. Then another sum, only one mode. Just NRL sum is by itself, like absolute sum. Then acceleration response, we got that. Then now you can design the hold down bolt. So like a tensile area of 3/4 bolt, 3/4 inch bolt we pick, right, from the beginning. Then tensile area is you have a thread already in the bolt. You have to subtract the thread depth, okay, to determine the tensile area. Where you find it? Any machine design book, you can find the table, okay? Like a Shigley's book. It's available in the library. Some old copies, I asked Yonok to find the one. So you found the one, Shigley's book. But all the new doesn't matter. Or any machine handbook, you can have bolt spec. When you look at the bolt spec, it's a tensile area is always spelled out there. Then total tensile area for 8 bolt, multiply 8. Assume the bolt, the ultimate tensile strength is 150,000. There is a different kind. If it's higher, it's more expensive. Then maximum bolt loading should be something like 90% of ultimate tensile stress. So you deduct 10%, so it's 135 psi, 135 kpsi. Then you have to check whether the bolt is okay or not. So this area it's like a machine design area, okay? So then it's okay. This is lower than 135, it's okay. So it's like, is bolt gonna stay, or bolt gonna be break by tensile loading? This is only considered the tensile loading. You have to also check the shear situations when the shock is in the authorship directions. Okay? Okay, second problem is also a single degree of freedom system, and you can I'll quickly go through. This is the case. Equipment sitting here. Then you have channels. It's coming like this. You have a pad here. You have a girder there. Then check the shock adequacy. What that means is it going to fail by the shock or not? So you have to check the safety for girder and the bolt and all that. So this is the input data. Surface ship, Class A, vertical shock loading, hull mounted, equipment weight, support foundation frame is 8, wide flange 31. Do you know how to read this? This is, if you look at the steel construction book, go check it out. If you work as a designer, steel construction book. It's from AISI, American Institute of Steel, SSC, construction. It has all the wide flange, any kind of the commercially available material. Then wide flange shape is like this, or I-beams. They have everything. It's a tube, whatever, and channels, all kind, about 200-page kind. So It's good book when you design. Maybe Yongwon may know, may not know. Okay. So so you have, then it has a moment of inertia of the section by XX. This is YY, and I think this is like XX. This is like YY, as I believe. Cross-sectional area is all available. Okay. Then you have to make a discrete model. Again, this is mass and spring. This acts as a spring, girder, mass. Some of the mass goes here, this plus that, and some of the girder mass, you have to consider it. Then you can determine the delta by the P. You know this, the P loading, for the loading P, then you have delta deflections. Then you can take a look at the steel construction book to get this result, or static analysis or strength of material book will get you this, or you can derive it whatsoever. The relation between delta and P, okay? So length L, E, Young's modulus, IXX is moment of inertia of the cross section for the girder. Then K is P over delta. Then you can determine the K. Then the weight, I use equipment's weight plus half of the foundation weight. Half of the foundation weight, half of this girder. Then you can compute the natural frequency. Same thing. Modal participation factor, single degree of freedom system is 1. Modal mass, modal weight. Then you determine the shock design factor by 1396. You have in the chapter 8 section. Then you determine the D1. It happened to be 140 G. Okay. Then effective static force, because you convert by DDEM dynamic stuff into the equivalent static, so huge loading. Then again you can consider the hold down bolt. Okay, and you have to check also the whether the girder is going to be okay or not. You have to check the size. Then you have to do that. Okay, next one is important. 2 degrees of freedom model. This is in Navy report. All this, the example problem 1, 2, 3, okay, is in the Navy report, unclassified report. One pump is a stick amount, motor is a stick amount. This is equipment, 3,500 pound. Then this is a hold down bolt, you have to design it, of course. Then there is a bolt connected to the equipment. And this is motor is running. This is 12-inch stick amount. The length is 12-inch. Motor is 500 pound. Mass is here. This is acting as the spring stiffness. Okay, and 48-inch long. Then our design is here. So whether equipment is good or not, bolt and the bolt right at the motors and bolt in the base. So 2 degrees of freedom model, you can consider that plus that. This will be okay. We know it's okay. If it's not, then you have to design for it. Then I can set the 2 degrees of freedom model like this. M1 equipments, M2 motors K2 is a stiffener for cantilever beam, and the K1 is for the girder. Okay? So now you are dealing with a 2 degrees of freedom model, and this cross section is for cantilever tube. Okay? This is really made up problem, but explains the DDAM procedure really well. Then you have to determine M1, M2, K1, and K2. So here is a cantilever beam. Then you have to determine the stiffness, and you have to determine K1, which is really coming from the girder. Use your engineering judgment. That's what that is. Okay? So all the data is available. Surface ship is given. And the foundation support beams, all given here. This is for this guy, for this. And this is a 2 degrees of freedom, mass M1, mass M2. I said weight of the equipment plus half of the support beam. You could argue why half. I feel that's about 1/3. Okay, I said okay, do it. Design is personal. Analysis is not personal. Design, you make a decision, not I. Sometimes you could make a disastrous decision, but with engineering background, you wouldn't do that. And M2 is weight of the motor and the portion of the motor shaft and some attachments, so you can do that. So I pick out this as 3531, and W2 is 600 pounds divided by the G, then you will get the mass. G is 386 inch per second square. Then you determine K1. This is for cantilever beam situation, and this is for fixed beam situations. Fixed beam situation. Then 2 degrees of freedom model. Then mass matrix is M1, M2. Stiffness matrix is K1 plus K2, K2 minus K2 minus K2. Can you do that? Willis, can you do that? Of course. You have done even 3 degrees of freedom system. And remember, this DDAM stuff is for initially for few degrees of freedom model, but nowadays they are using how many degrees of freedom model? Million degrees of freedom model. Something wrong, right? Well, they don't know what's the history behind it, but seems to be working, so that's what they are using it right now. This is a free vibration equation. Then you have to solve this for eigenvalues and eigenvector, or simply the natural frequencies and mode shape. This is, I want you to go through, we went through using 2 degrees of freedom model. You know, right? So then you determine that. You determine for omega 1 and omega 2. This is the first natural frequency. This is second natural frequency. And this is in radian per second. And you can convert into, if you divide by 2 pi, then you can get the hertz or cycle per second. Then corresponding mode shape. You know already mode shape. First mode is in phase. Second mode is out of phase. So that's what, in other words, the equipment here, the motor is stick them out. In phase is as it goes up, it goes together. But for the second mode, not in the same direction. If it goes up, it goes down like this. Then you can exactly the same way. I'm not going to bother. Then phi1, phi2, omega 2. Then this is not normalized. Okay. So then phi matrix, you can have that. First mode, second mode. Then modal participation factor. Modal participation factor, then if you get that, 0.945, 94.5% is going to take by including just one mode. Okay, that's enough. What's the criteria? 80% criteria, but this already met 94%. Then all you have to do here is include only one mode. Okay, but for the fun, well, we compute P2 is this is what 0.05%. So second mode contribution to the loading is almost none. Okay, then you compute the modal mass and all that. Then go. It's very systematic. This I call the cookbook. Very, very systematic. From the 1396, you pick out all that, then determine the shock design value. The shock design value, so use 247.4 G, which happen to be a lower. Then you compute the equivalent static loading F11, F12, F21, F22. You compute F4. This is a mode. In fact, you don't need to use a two mode, only one mode. But we just for kick, we gonna do, it's only two mode system, so include the two mode. This is a DOF. So you compute, I compute F11, F12, F21, F22. So first you apply this guy as a first mode, and this guy is a second mode. Okay? To the system. So for this model, it goes like in phase. You can say it goes up, right, statically here, but you can apply the loading the other direction, which is compressive. This is tensile. Usually for carbon steels, any kind of a steel, the compressive stress, allowable compressible stress is higher than really tensile stress, but regardless, you can apply in tension or compression. Okay, and for second mode, is in the outer phase this way or that way. Okay, so that's what you have to do for actual the model, actual system, in phase, out of phase, or you can apply downward. Here is opposite. One goes down, this guy go up, like this. So you have to check after this, once loading is determined, after that, that's a static problem, right? It's a static analysis problem, right? Say yes. That's what you have to solve. Static analysis. Everybody has done the statics and dynamics course. Mandatory. Right? Okay, so then after that, check the stresses, doing NRL sum. For two mode, NRL sum is sum of absolute values by itself. Okay, and chapter 9.4 is same as appendix. So appendix is chapter 11. So really doesn't. This section 9.5 shock design criteria for the surface ship is published in 1994. This is the year that Kim in the KIMM, Korea Institute of Machinery and Matters, Dr. Chung Jong-hun, he was out in the shock and vibration symposium that year, I know. He picked out this report, unclassified report. I think he still has it. I have it somewhere. But it's a thick book. Then I really scanned through and made this PowerPoint, not the PowerPoint. Oh, it's a PowerPoint? Anyway, documents to read easy. So chapter 3 only, that's all you need. So you don't throw away as long as you do the shock. For equipments, this might be good idea to use in the future. Okay, so all the relevant spec for shipboard equipments are all here. So that's what this particular section is, and also appendix 11 is the same thing. Okay.